So students, can you hear me? So can you hear me and can you see the screen? So please do type in the chat box. Can you hear me and can you see the screen clearly? Yes? Fine, good evening. There's small network issue. I think you can hear me, correct? And you can see the screen. Yes? Yes. Okay, so you can hear me. Good. So, yeah, it got delayed a bit. So, in today's class, we'll solve some practice questions on previous GATE year questions and, previous year GATE questions basically on this capillarity and this fluid statics. So, shall we start solving? So, please do type in the chat box. So, shall we start solving? I hope there is no issue. You can hear me, correct? Fine. So, let us look at the first question, which we have already seen last time. So, let me quickly go through the question once. So, let us quickly go through the question. So, in the space above the mercury column in a barometer tube, the gauge pressure of the vapor. So, he is asking about the gauge pressure of the vapor. So, what are gauge pressures? Gauge pressures are the pressures which are measured relative to this atmospheric pressure, local atmospheric pressure, correct? So, if you take a barometer, how was the construction of barometer, which I have given you initially when I was taking the course? So, if this is some mercury, so if you invert a glass tube in this, then what happens to this mercury? It raises to certain height, okay, in this glass tube, and this height is found to be 76 centimeters of Hg under normal atmospheric conditions. So now it's given, if this is the vapor of mercury which is present here, we know that this vapor pressure of mercury, this vapor pressure of mercury is almost zero, very small, correct? So now we know P atmospheric pressure local, this will be equal to PV plus, if this height is rho GH, of course this is rho mercury, G is 9.81 and H is 76 centimeters, which is 0.76 meters, then we know this is rho Hg into GH, correct? This is what we have. So if you see this PV, the space above the mercury column in a barometer, so this is the mercury column and the space above this. So here, if you see here, then definitely this P vapor pressure is equal to P ATM local minus rho mercury GH, correct? This is what we have. Yes. Pole option is not yet available, Rahul. So we are looking. So please try to look here. So this is the case. And we know some pressures which are less than atmospheric pressures, they are called as negative gauge pressures or vacuum pressures, correct? So here he is asking for the gauge pressure of the vapor is. So in terms of gauge, if we talk, we call that as negative gauge pressure, because this pressure PV means the pressure of this space above this mercury column is less than atmospheric pressure. So this is a negative gauge pressure. Negative gauge pressure, correct? Or you can also say vacuum pressure. Vacuum pressure. So you can see any of these things, and this question has this negative as the correct answer because the gauge pressure is negative, correct? So this is what we have seen in last class. So are you clear so far with this question? This is a simple question, of course. The only thing, if you know, identify the difference between absolute pressures and of course gauge pressures, then you can easily answer this question. The answer is positive only when you are talking about absolute pressures, because here this PV is very small, of course, but it's a positive value when you talk in terms of absolute. But now you see this is less than atmospheric pressure, so this PV is called as negative gauge pressure, correct? Fine. So let's go for the next question quickly. So let us go for the next question very quickly. Okay, so this is the next question. So please see here. An inverted U-tube manometer is used to measure the pressure difference between two pipes A and B as shown in the figure. Okay, you can see there is one pipe which is carrying some oil and there is another pipe which is carrying some water. Fine. So there are two pipes which are connected to this inverted U-tube manometer. Pipe A is carrying oil. You can see here pipe A is carrying oil whose specific gravity is 0.8 and pipe B is carrying water. So specific gravity is 1 because we generally measure it with respect to water. The densities of air and water are 1.16 kg per meter cube and 1000 kg per meter cube. Okay, because in an inverted U-tube manometer, you know that you will be using pressurized air as your manometric fluid. So definitely this density of air is given 1.16 kg per meter cube. The pressure difference between pipes A and B is dash kilopascals. take acceleration due to gravity g is equal to 10 meters per second square. So quickly try this question, because let us try this question. So this is an inverted U-tube manometer. So definitely if you take any point here, this is the point in the air manometric fluid. So the pressure in both this left and right directions is equal in this case, correct? So this is a common air column till here. So if you take a reference section here, XX, then definitely about this section, this air should maintain a static pressure balance. So definitely if you consider the pressure at this point A and at this point B, then you can easily identify pressure at, okay, or else let us not call the points as A and B. So see here, let us call these points as C and D, for example. So if you talk the pressures at C and D, definitely, this is filled with oil. So if you want to know the pressure at this point, then you can write, if you calculate this left limb pressure, what is the pressure at this point because of this left limb fluids. So this is PA. So PA, which is the pressure of oil, and you see this is the horizontal column, and in a horizontal column pressure doesn't change. So this oil is rising to a height of 200 mm, correct? So we are going in the positive direction of z axis, correct? So we are going vertically upwards. So if we are going vertically upwards, pressure starts decreasing. So that's the reason why we put a minus sign here. Minus O oil. What is the density of oil given? Specific gravity is 0.8. So I am writing this O oil as, okay, O oil G into this height is 0.2 meters because it's in mm. So let us write it in 0.2 meters, 0.2. And there is also some air column here, and the density of air is also given. Of course, the value will be very small, but still we need to consider because some data is given in the question regarding this air. So minus density of air into G into, this is 80 mm, so 0.08 meters. And this should be equal to, at the same horizontal plane, if you go from the right limb, there is continuous water from this horizontal plane to this horizontal plane. There is continuous column of water, correct? So what we can write in the right limb, PB minus, it's going in the positive z axis. So definitely pressure starts decreasing. So O water into G into, and what do you have? 100 plus 200, which is 300 plus 80. So 380 mm, so which is 0.38. This is what we have, correct? So this is what we have. So here we know some values. Let us write the known values to us. PA we don't know, but density of oil is known to us, 800. G is known to us. This is 10 meters per second square. Again, density of air is given 1.16. G is also given 10. PB is not known to us. Density of water is 1000. It's given already, and G value is also 10. So let us calculate the difference between PA minus PB. Okay. So if you calculate the difference between PA minus PB, let us see what's the calculation. Because in question they didn't mention clearly PA minus PB or PB minus PA. They are asking you for the pressure difference between the pipes A and B. So let us calculate PA minus PB. So if you calculate this PA minus PB, this first of all, this density of oil into G into 0.2 will go on to the right hand side. So 800 into 10, which is 8000 into 0.2. So 8,000, you can write this is 2, so 1600 on the right hand side, correct? So this is 2 into 800, 1600 plus 1.16 into 10 into 0.8. So this can be written as 1.16 into 0.8 minus, this will be here as it is. So minus density of water is 1000 into 3.8, and this value which you are going to get is in pascals, correct? So let us calculate this value, and the value which you are going to get is in pascals. So let us calculate, take the help of a virtual calculator, and let us quickly calculate this value. Okay, so let us calculate this. So now this is the virtual calculator that you see in your exam. So let us calculate this. 1600 plus 1.16 into 0.8. 1600 plus 1.16 into 0.8. This is what we have. Minus we have something 1000 into 3.8. So that's nothing but 380, correct? So minus 380 or 1.6. How much is the value? Sorry, 1000 into 3.8. So 3800. Actually, this value is 3800. So let us cancel this one. 1600 plus 1.16 into 0.8 minus 3800. So if you calculate this, minus 2199.072, minus 2199.07 pascals. So here they are asking you the answer in kilopascals, correct? So this much pascals is equal to PA minus PB is equal to this is in pascal. So if you convert this into kilopascals, your answer will be minus 2. Did they ask you to round up? They didn't ask you, but generally if you round up, this can be written as minus 2.2 kilopascals, correct? So PA minus PB is minus 2.2 kilopascals, and you can see the answer minus 2.21 to minus 2.19, which is minus 2, which is containing the value minus 2.2. So this is the correct answer. So have we got 0.38? Look, this is 100, this is 200, because this is continuous water column from this section to this horizontal section. This is continuous water column. So 100 mm plus 200 mm plus 80. Total 380 mm. So 380 mm corresponds to 0.38 meters. Okay, Rahul. So that's how I have multiplied a 0.38 here. So the value is minus 2.2 kilopascals. In examination, they didn't ask you for the, they didn't ask you basically, means they didn't mention PA minus PB or PB minus PA. So that year in the final answer gate, I mean in the final key that was given, it's also given minus 2.21 to minus 2.29, or it's also given 2.19 to 2.2, because if you write PB minus PA value, this answer will turn to 2.2. Okay, so that's the reason. Clear? So is that clear to all of you? Are you all clear till this point? If you are clear, then we'll go for the next problem. Is that clear? How did we get this pressure difference basically? Yes? So please do type in the chat box. So did you all get how did we solve this question? Okay, fine. So let's go for the next question. So this is one question. Assuming constant temperature, okay, condition, and A to be an ideal gas. So A to be an ideal gas, this is also the assumption. The variation in atmospheric pressure with height calculated from fluid statics is. Can you answer this question directly? Did I give you some data for this? Yes or no? Did we give any derivation and some idea of this pressure variations in incompressible fluid, compressible fluid with isothermal condition, and incompressible fluid, I mean also compressible fluid with non-isothermal condition? Did I give you? Yes or no? So let us write the relations once again. So in case of incompressible fluid, pressure varies linearly. This is what we have seen. Correct? So in case of a compressible fluid, or you can write a isothermal compressible fluid, better. In the case of an isothermal compressible fluid, we got, can anyone tell me, this is the question that they are asking me for. We got exponential. Very good. Very good, Vienna. So exponential. This is what we have got here. Correct? This is exponential. And in case of non-isothermal compressible fluid, and in case of this non-isothermal compressible fluid, we got the variation. What's the variation that we got? It's a power law kind model. Correct? I gave you the derivation for this already. So this is power law kind model. Okay. So these are the three variations, and in this case, he is asking you for this ideal gas, and of course, which means a compressible fluid, and of course, assuming constant temperature. So in this case, this is the correct choice, and your exponential is the correct choice. Answer B. Yes, it was the question from GATE 2014. You can see there clearly. Yes, B is the correct answer. Oh, I think you are not able to see some screen. You can refresh the tab. Okay, because I am also watching it in my mobile, so it's going fine for me. Okay, so I hope there is no issue. Good. Let's go for this next question. A two-dimensional fluid element rotates like a tau is equal to 0 rigid body. At a point within the element, the pressure is 1 unit. Radius of Morse circle characterizing the state of stress at the point is. So they are asking you, whenever a fluid is rotating like a rigid body. So there is a fluid element. And this fluid element is rotating like a rigid body, which means one thing is clearly given, shear stress is equal to 0. If shear stress is equal to 0, then can you tell me what is the radius of this Morse circle? And of course, it's given inside a static fluid, correct? So a two-dimensional fluid element rotates at a point within the element. So they are asking about at a point within the element, the pressure is 1 unit. And if I talk that the pressure is 1 unit, that means pressure is same in all the directions, which means my sigma xx and sigma yy both are same. Means the two normal stresses that are acting on this cube are same. Means basically on this element are same. So in that case, what is the radius of my Morse circle? Tau max, if this is minus p, and of course this is also minus p, and your tau is equal to 0. So in that case, what is the tau max? Means basically what is this radius of Morse circle in this case? Radius of this Morse circle is equal to, tau max is equal to, what's the answer? What's the answer in this case? If shear stress is 0, see, it's clearly given, shear stress is 0, tau is equal to 0, and at a point at which the pressure is 1 unit, and it's clearly given at a point. So at a point, definitely pressure is same in all the directions. So which means all your normal stresses are same. So your tau max is equal to What's the answer? Your tau max is equal to 0. You remember, I was telling you, in case of a static fluid condition, the Morse circle reduces to a point, and of course, if you try to draw this Morse circle, it looks something like this. This is the normal stress axis, and if this is the shear stress axis, then you can see the Morse circle is just a point, correct? And the distance of this point from this tau axis is minus p. I mean, this is distance, so let us write p, but it's on the negative side. Okay, so this is what I have told you, correct? So clear? So shall I go for the next question? Yeah, it's an interview question, correct? That was asked in a different way in this GATE examination, okay? But the concept or the ideology is same behind both. Fine. So shall I go for the next problem? Shall I go for the next problem? Is that clear to all of you? Fine. So let's see here. The pressure gauges G1 and G2 installed on the system shows the pressures of Pg1 is equal to 5 bar. So this fellow is reading 5 bar. And what about this gauge reading? This is reading 1 bar, 1.00 bar. Okay, fine. And I think this is also 5.00 bar. Okay, this is 5.00 bar. Okay, fine. So now the value of the unknown pressure P is the value of this unknown pressure P, and it's clearly given atmospheric pressure is 1.01 bar. Okay, fine. So when this atmospheric pressure is 1.01 bar, look, means outside the pressure is 1.01 bar and the gauge is reading 1 bar. So if you want, what is the pressure inside this chamber, actual pressure inside this chamber, P actual in chamber is equal to, so if you want the actual pressure inside this chamber, look, these gauges, they always give the gauge reading depending upon the local atmospheric pressure. I told you clearly, correct? So if this pressure which is surrounding this gauge is 1.01 bar and still this gauge is reading 1.00 bar, can you tell me what is the actual pressure inside this chamber? Forget about this gauge and this chamber again. So please try to tell me what is the actual pressure in this chamber. Look, this gauge always gives you gauge pressure and this is 1.01 bar is the atmospheric pressure. Under the action of 1.01 bar atmospheric pressure, this gauge is capable of reading 1 bar. So which means the actual pressure inside this is, what is the actual pressure inside this? I need your responses. I am waiting for your comments. So what is the actual pressure inside this chamber when gauge is reading 1 bar with an outlet with an a surrounding pressure of 1.01 bar? This value is nothing but, so the actual pressure is summation of these two, correct? 1.01 plus 1, 1.01 plus 1.00. So which is 1.00, so which is 2.01 bar, correct? So this is 2.01, correct? Yes, 2.01 bar. If this is 2.01 bar, again see, this gauge is surrounded by a pressure of 2.01 bar and this gauge, instead of, even though 2.01 bar is acting on this, and this gauge is reading 5 bar. So what is the actual pressure P in this case? Again this 5 plus this pressure which is in this chamber. So 5 plus 2.01 which is 7.01. 5 plus 2.01 which is 7.01 bar is the actual pressure P, correct? The value of the unknown pressure P, correct? So 7.01 bar. Yes or no? How does the gauge read pressure? Basically, if I put a gauge in 1 atmospheric pressure, then the reading obtained by the gauge is actually gauge pressure. So if you want to know the absolute pressure of the container to which this gauge is connected, then you need to add the gauge reading plus absolute reading, correct? You remember, to calculate P absolute, I told you P atmospheric local plus P gauge reading. You remember this? So gauge reading is given, P atmospheric is given. So we need to calculate absolute. And once you know the case, similarly you need to apply here to get the actual value, 7.01, correct? Yes, 7.01 is the correct answer. Fine. Are you all clear till this point? Did you all understand how it's 7.01? Because I have given you this equation. So at an expense of 1.01 bar atmospheric pressure, this gauge is still reading 1 bar. So which means the actual pressure to which this of the container to which this gauge is connected is, at this point the pressure is 2.01 bar. Similar is the case here. So at an expense of 2.01 bar pressure, this gauge is reading 5 bar. So which means the actual pressure of this is summation of this 5 plus 2.01 which is 7.0. Clear to all of you? So please do type in the chat box. Are you all clear with this? So please tell me, are you all clear with this? This plus can be put in a proper order. So So are you all clear with this question? If you are clear, then we'll go for the next problem. Clear? Good. Look, let's go for the next problem. A static fluid can have, I think this is a simple question and of course a bit old question as well, some 17 years ago or 18 years ago almost. So please try to solve this. A static fluid can have, what can a static fluid have? Can a static fluid have shear stress acting on this? Can a static fluid have shear stress acting on the layers? If the complete fluid is static, can the fluid suffer and can the fluid be acted upon some shear stress? No. So a static fluid can never have some shear stress. So these two options are wrong because in this option shear stress is given and in this option non-zero shear stress is given. Correct? Now, so zero shear stress is given in both these options. Okay, fine. A static fluid can have positive normal stress or negative normal stress. Compressive forces means pressure is basically compressive or tension. So please tell me, pressure is basically positive normal stress or negative normal stress basically? It's negative, correct? Because pressure is always normal, external and compressive force that's acting per unit area, correct? So definitely this positive is wrong and negative is correct. So B is the correct answer in this. Negative normal stress means compression, that's it. So B is the correct answer. Yes. So B is the correct answer. Negative normal stress and zero shear stress because it's a static fluid. And in a static fluid, I told you clearly, in a static fluid, at this point, if you take any point, if this fluid is static fluid, then I told you clearly this tau is equal to 0 and definitely sigma x is equal to sigma y is equal to minus p. Correct? This is what I have given you. You remember this equation? So definitely it can suffer some negative normal stress. Negative normal stress. And of course, this is 0 as usual. Fine? Yes, option B is correct. So shall we go for the next question? Let's quickly try to solve this question. So shall we go for the next question? Shall we go for the next question? Are you all clear till here? Fine? Yes or no? So please do type in the chat box. Are you all clear till here? Please do type in the chat box, students. I hope this question is clear to you, right? If you are clear, yes, then we'll go for the next question. So I think again something is given. So some diagram is given, so fine. In the given figure, if the pressure of the gas in the bulb A is 50 centimeters of Hg vacuum, so this is 50 centimeters of Hg vacuum. So what is the actual pressure or the absolute pressure in this gas bulb? So P ABS of the gas bulb. P absolute is how much? It is given 50 centimeters Hg vacuum, but you know atmospheric pressure is 76 centimeters of Hg. Then the height of the column H is equal to. So can anyone tell me the answer? Can anyone tell me the answer? See, this is given 50 centimeters of Hg vacuum. So which means this is 50 centimeters Hg vacuum pressure, which means this absolute value is atmospheric pressure P atmospheric local minus P vacuum pressure. Okay, so this value is equal to 76 centimeters of Hg. Of course, I am writing in terms of centimeters. So 76 centimeters of Hg minus this bulb is given 50 centimeters of vacuum pressure. So 50 centimeters of Hg. So totally what is the absolute pressure here? P absolute of this bulb is equal to 50 centimeters of Hg. 76 minus 50, which is 26 centimeters of Hg. It's 26 centimeters of Hg. This is what you have. Fine. So if this is 26 centimeters of Hg, and here at this layer totally if this is 76 centimeters of Hg, look, this total has to be 76 centimeters. This PA plus this total thing, this has to be 76 centimeters, correct? And now we came to the conclusion that the pressure because of this bulb, or if you neglect this total is 26 centimeters of Hg. Then what will be this value? If this is 76, you know that's 26. So what could be the value of this capital H? What could be the value of this capital H? So please tell me what could be the value of this capital H now. You came to the conclusion that this absolute pressure of this bulb is 26 centimeters of Hg and absolute pressure of atmosphere is nothing but 76 centimeters of Hg. So this height should be equal to 50 centimeters of Hg basically. this height should be equal to 50 centimeters of Hg, okay? Because absolute pressures we balance generally, so this is the case. 50, correct. You need to read the question carefully. See, it's given pressure of the gas bulb A is 50 centimeters Hg vacuum. So vacuum pressure is measured in terms of centimeters of Hg. So absolute value is 76 minus 50, which is 26. Clear? Okay, so let's go for the next question. So here is some question, some old question a bit. A mercury manometer is used to measure the static pressure at a point in a water pipe as shown in the figure. The level difference of mercury in the two limbs is 10 mm. So this difference is 10 mm. Fine. If this is 10 mm, then if this is 10 mm, the gauge pressure at that point is. So where is that point? A mercury manometer is used to measure the static pressure at a point in a water pipe as shown in the figure. So let us suppose if this is the point. At this point we are measuring the pressure. The level difference of mercury in the two limbs is 10 mm. The gauge pressure at that point is, okay, fine. So this is water and this is 10 mm. So please try to solve this question. They are asking you the gauge pressure at that point is. So basically they are asking you for this gauge pressure at this point. This is open to atmosphere. So please try to solve this question. So please try to solve this. So please try to solve this question. It's given there is the water that's flowing to the pipe and there is some, of course, because of this pressure at this point, there is some deflection in the mercury and this difference between these two pipes is 10 mm. So please try to calculate this. Gate mechanical 96. Okay. So if you see, but how to identify this water column weight? Height. How to identify this capital H? If you can identify this capital H, then that's okay. Correct? So anyhow, let us go for the nearest value. So see here. The pressure at this point PA means if you apply your equilibrium about this section XX. So now see carefully. PA plus rho water G into H plus 10 mm. So H plus 10 mm is nothing but 0.01 meters. So this should be equal to P atmospheric local because this end of the manometer is open to atmosphere. So this end is open to atmosphere. So this is equal to P atmospheric plus this water column is again 10 mm. So density of mercury into G into 10 mm. 10 mm is nothing but 0.01 meters again. So if you calculate few values, so PATM minus PA minus PATM, which is nothing but gauge pressure at A. This is equal to rho Hg of mercury. So density of mercury is nothing but 13,600 you can take. So 13,600 into G, let us suppose if you are taking 9.81 into 0.01 meters minus density of water into G into 0.01. So density of water is 1000 into 9.81 into 0.01. So let us suppose if you are taking this value, because this H is generally very small when you compare to these columns and this pipe diameters and all. So let us suppose if you are neglecting this H value because it's not given. So that small difference when you compare means this density of Hg is 13.6 times, 13.6 times of density of water, and generally if this H is very small, if you assume this, so 1260 into 9.81 into 0.01. So let us calculate this value. 12,600 into 9.81 into 0.01. So let us calculate this. 12,600 into 9.81 into 0.01. So if you do this, 1237.32. So if you see 1237.32, so 1236 could be nearest answer to this. Okay, approximately, because in gate you can always choose the most appropriate answers. So PA minus PATM is equal to how much did we get? 1200 and something we got 1237.32. So 1237.3 pascals because this value is in pascals. So you can observe one thing here, the value is given 1236 because this density of water is very small as not very small but considerably small as compared to this density of mercury, correct? So if you subtract this minus 1000 into 9.81 into some other little small value as compared to this 0.01, this value will slightly reduce. Okay, so 1236 could be a correct answer. Okay, reasonably. Is that clear to all of you? Fine, is that clear to all of you? Yes or no? So please do respond. Is that clear to all of you? I think this is a very old question. Okay, 96 something. No? Fine. So is that clear to all of you? 1237.3 pascals. That's what we got. Final answer. Yes? Okay, let's go for the next question. Okay, so let us try to solve this question. The figure shows a U-tube having a 5 mm by 5 mm square cross section filled with mercury. So basically this tube, cross section is given, it's 5 mm by 5 mm. So this value is equal to 25 mm square. So 25 into 10 to the power minus 6 basically. Correct? So 25 mm square. So which means 25 into 10 to the power minus 6. 25 into 10 to the power, if you deal in case of centimeters. Anyhow, so let us deal in meters only. So this is meter square. Because 1 meter is mm is equal to 10 to the power minus 3 meters. Fine. This is okay. So area of cross section is equal to this value. Now see clearly what's happening. This is filled with mercury of specific gravity 13.6, okay, up to a height of 20 centimeters in each limb, open to atmosphere. So definitely whenever there is no pressure, means basically whenever this manometer is free, then definitely the mercury level in both the limbs will be same, correct? As you are saying in this case. So this mercury level is same initially because there is no connection to this manometer. Fine, this is okay. Now see what's happening. If 5 just a second. So if 5 centimeter cube of water is added to the right limb, so what's they are doing? They are just putting in some 5 centimeter cube of water. 5 centimeter cube of water is what they are putting. So if they are putting 5 centimeter cube of water inside this, what happens? Definitely there will be some column of water in this, but because of this water column, there exists some pressure difference between both the limbs. Yes or no? Do you all agree? Look, this question is a very nice question, so please see here. If 5 centimeter cube of water is added to this right limb, then what happens? Because of this pressure due to water column, this mercury level which is in the right column slightly gets down, and by the amount which this mercury level gets down, the same amount it will go up, correct? So let us suppose the new configuration is, in this case, let us suppose the new configuration is, let me take the help of some drawing tools. Okay, fine. So see here. Okay, so see here, I'm attempting to draw one YouTube manometer as I have shown you. So fine. So let us suppose this is the manometer. So initially the level of mercury is same. So let us suppose the initial level of mercury in both the limbs is somewhere here, 20 centimeters. Okay. So let us suppose this is the initial level of mercury. Now, because of this addition of 5 centimeter cube of water inside this, means if you add 10 centimeter cube of water, what happens? Definitely, because of this water pressure, this mercury level which is initially here gets depressed a bit. Let us suppose to this level it is getting depressed, okay, and this is filled with water. No, if this is the amount x which is in the depression of this mercury, which is initially at this level, now it has come to this level. So basically this is the level of mercury. So let us suppose I am denoting this mercury, something like this, okay. So let us suppose I am quickly drawing this mercury in this tube. So see here, I am trying to draw mercury. You can also draw in your book because this is a very good question. So see here, we are trying to draw some mercury in this. Correct? So see here. And if there is x depression here, definitely there is some x elevation here in the left limb because total volume of mercury is constant. So if there is some x depression on the right limb, definitely there will be some same amount of elevation in the upper limb as well. Correct? So let us suppose if this is the new level of mercury in the left limb. Okay, so this is your mercury which we are trying to fill in general. So I'm just drawing a freehand sketch. So please see here. If this is mercury, fine. So this is mercury, correct? So this is how, if there is some x deflection here because of this water column, definitely there will be the same x elevation here. This is one thing known to us. Now, and definitely this height won't be equal to this mercury column because obviously the specific gravity of mercury is high, so it elevates only to a little extent. So now see here. Let us suppose now we are considering a section about this plane. Okay, this is new plane, so x. Let us suppose this is x. So if you apply the pressure static balance about this, we will get to know what is the height of this mercury. Initially this height is 20 centimeters in both the limbs. 20 centimeters of mercury is available in both the limbs. But now, because of this addition of water on the left hand side, there is some elevation in the mercury column. Did you all, first of all, let us forget about the static equations. But did you all understand how this is happening? If you pour some excess liquid here of water or something, because of this pressure developed by this fluid column, there exists some pressure on this mercury and there is some depression in the right limb of mercury, and whatever is the depression, same depression gets, this depression which is here gets elevated at this left column. Are you all clear till this logic? Are you all clear till this point? First of all, if you are clear till this point, then we'll go for the next question. Are you all clear till this point? Yes? So please do type in the chat box. Did you all understand when you pour some mercury, when you pour some liquid on the right limb, definitely there is some depression because of this pressure column, and that depression in this mercury in the right limb is equal to the elevation of mercury in the left limb, correct? If this is the case, now let us apply the static balance about this. Initially this height is 20 centimeters on both sides, correct? Because you can see clearly this height is 20 centimeters initially in each case. But now, because of this mercury, what they are asking, the new height in centimeters up to 2 decimal places of mercury in the left limb will be, look, means he is asking you for what is this value, total value. If this is the reference, then what is this h value, correct? This is what you know, means if you can find what is this value, that's it. Means basically if you can find what is the value of this x, then story is done. Look here, let us, since both sides are open to atmosphere, so let us apply the static pressure balance. So if you apply for the left limb, what do we have? P atmospheric local plus density of mercury into G into this mercury column is of height total 2x, correct, about this reference plane, because this length is x and this length is also x, so total x plus x will give you 2x, and this should be equal to, if you equate the pressure on the right hand limb, P atmospheric local again plus he is pouring some water, so density of water into G into, and this density of water is totally this height plus this x. Now what is this height? Or else you can identify, if you call this total height as capital H, what is the value of this capital H? Let us identify. You have seen clearly volume added is equal to 5 centimeter cube. 5 centimeter cube is nothing but 5 into 10 to the power minus 2 whole cube, which is 10 to the power minus 6 meter cube. Correct? This is what we know, 10 power minus 2 whole cube, 10 power minus 6. So if you want to calculate h, this h is nothing but volume divided by the cross section area. So this is the total height to which this mercury will, to this water will rise up. So this is 5 into 10 to the power minus 6 divided by 25 into 10 to the power minus 6. So this is 0.2 meters, which is some 20 centimeters. So this h value is 20 centimeters. This is clear to us. So if you solve this question, then into 20 centimeters is again 0.2. Let us calculate x in meters only, because Ph.D we are substituting, plus that's it. So this is 0.2 meters. So now if you calculate the total things, P atmospheric and P atmospheric gets cancelled. So this implies density of Hg into G into 2x. This is equal to density of water into G into 0.2 meters. So now you can cancel this G and G both sides, and the specific gravity is 13.6, so 2x is equal to, or else you can cancel 1, 2 maybe. If you can cancel 1, 2, this will be 0.1. Okay, so x is equal to density of water by density of mercury into 0.1. So let us calculate this value, correct? Which is nothing but 0.1 divided by 13.6, correct? Because this can be written as 1 by 13.6, correct, into 0.1. So let us calculate this value. 0.1 divided by 13.6. So 0.0075 meters. So if this is in meters, means 7 mm basically, this is around 7.35 mm, which means 0.75 centimeters, correct? So this value is 0.75 centimeters, correct? This is the actual value. Fine, 0.75 centimeters is the x. So if this x is 0.75 centimeters, then what is the total height h? This height h is equal to 20.75 centimeters is the total height of Mercury in the left limb. So are you all clear here? Yes. So this h is equal to 20.75 centimeters. Clear? So are you all clear till this point? And what's the official answer given? Yes, 20.70 to something. Yeah, okay, fine. 20.70 to 20.75, I guess. Okay, so anyhow, the answer is 20.75. But this is a nice question. Okay, so we didn't do anything here. We just identified if you pour this much volume of water into this tube, because of this cross section, what will be this height of this water column? We have found that. So once you have found what is this height of water column, just a static pressure equation. That's it. New height is 20.73 centimeters. Correct. 20.75 is what I got when I calculated. Okay. Okay. So is that clear to all of you? Shall I go for the next question? Is this clear to all of you? Did you all understand this question? So please type in the chat box. Did you all understand this question? Are you all clear till this? Yes. Any doubts to anyone at this question? Because this is a good question actually. Fine. Okay. Let's go for the next question. Okay. Something is given. 3 rigid buckets shown in the figures 1, 2 and 3 are of identical heights. This 1, 2, 3 are of identical heights and identical base areas. Okay. Of identical heights and base areas. Which means here they are not down up to the scale, but the base areas are same. Okay. Means the length of this, I mean, it's not down to the scale, but of course it's given in the question that all these 3 base areas are equal. Okay, fine. Then what is the question? Further assume that each of these buckets have negligible mass. Okay, fine. And full of water. Okay, this height h is same in all the case, and all these 3 buckets are full of water. The weights of the water in these buckets are denoted as W1, W2 and W3 respectively. Also, let the force of water on the buckets on the base of the bucket be denoted as F1, F2 and F3 respectively. Okay, the option given an accurate description of the system physics is. The option giving an accurate description of the system physics is. So basically they are asking me about a comparison between forces on the base and also weight of the water. So first tell me one thing. In hydrostatic law, I have told you something called the hydrostatic paradox. Means whenever there is fluid column of height h equal height h in all the 3 vessels, can you tell me if I call the pressure as P1 at this base, P2 at this base and P3 at this base? So can you tell me what is the relation between P1, P2 and P3? So please tell me, can you tell me the relation between P1, P2 and P3 as per the hydrostatic paradox I gave you? Look, all 3 are water and all 3 fluid columns are of equal height h. So can you tell me about P1, P2, P3 relation? Can anyone tell me P1, P2, P3 relation? Please do type in the chat box. Can anyone tell me about P1, P2, P3 relation? If P1 is the pressure, P2 is the pressure, P3 is the pressure here. P1 is equal to P2 is equal to P3. Correct? All 3 are same. This is what we know. Now, once this is given, they have equal base areas. So force on base. Look, let the force of water on the base of the bucket is F1, F2 and F3. So can I write Fi? If Fi is the force on the ith bucket, then this is equal to pressure I into Ai, and it's given all the base areas are same, and now you know P1, P2, P3 are same. So these 2 parameters are same. So can you talk about F1, F2, F3? Can you talk about F1, F2, F3 now in this case? Because force is nothing but pressure acting into area. It's given all the 3 base areas are equal, and also you know P1 value is equal to P2 and it's also equal to P3. So can you talk about F1, F2, F3 now? Anything? All these 3 values will be same or different. So please do type in the chat box. I am waiting for your answers. F1 is equal to F2 is equal to F3. Very good. Correct? So because pressure is same on all the bases and also area of all the bases are same. So definitely F1 is equal to F2 is equal to F3, which means option A is wrong and option B is also wrong. Now, in these two options, you have F1 is equal to F2 is equal to F3. Fine, that's okay. Now, see carefully. They are also asking you for the weight. Weight is equal to gravity into density into volume. Correct? This is what we know. So, gravity is constant in all these three cases. All these three cases have water as the fluid, so density is also same. So, now, weight is directly proportional to volume. This is what we know. Correct? So, weight is directly proportional to volume of the fluid, of course, in incompressible case as well. So, now you can see one thing very carefully. Out of all these three, if base areas are same, can you tell me which bucket has highest volume? If I name the buckets as 1, 2 and 3, if base areas are same, now out of these three buckets, can you tell me which bucket has highest volume? Can anyone tell me which bucket has highest volume here? 1, 2 or 3? Assume this all three base areas are same. Second has highest volume, correct? Obviously, because if this base area is equal to this base area and if this is diverging, that means it's carrying more fluid. So, out of all these things, W2 is more. Now, if these two base areas are same, then definitely volume obtained in this cylinder is more. I mean, in this bucket is more. So, next followed by W1 and finally by W3, correct? So, W2 greater than W1 greater than W3. So, D is the correct answer. And obviously, weights are not equal in all the three cases, correct? You know this. So, D is the correct answer. Fine. Are you all clear with this question? So, are you all clear with this question? If yes, please do type in the chat box. Okay, fine. So, please do type in the chat box. Are you all clear with this question? Did you all understand how D is the correct answer for this? Yes? Very good. So, now let's go for the next problem. Okay, something is given. If a small concrete cube is submerged deep in still water, what is the meaning of still water? It's in static state without any disturbance. In such a way that the pressure exerted on all faces of the cube is P, then the maximum shear stress developed inside the cube is dash. This is what they are asking you for. Look, what they are telling you, what they are trying to tell you, see here. There is one cube. Okay, so there is one cube basically. And it's a small cube actually. Okay, so it's a very small cube. So this length of the side can be neglected in general. So if the length of the side can be neglected, then if this length of the side is neglected in general, okay, so this complete cube is in a bulk of static fluid. Static fluid, okay, so this is some static fluid on the top as well, okay, so and so I think now you can feel there is a cube here. So there is one cube. Now, normally, you know, if you go along the z direction, your pressure increases, but it's clearly given small concrete cube. This is cube is very small, and pressure exerted on all the faces of the cube is P. What's the meaning of that? Means the height of the cube or the side of the cube is very small, such that there is no pressure variation within that length of the side. Correct? This is one thing. So which means you can identify clearly the pressure on this face, similarly on this face, on this face, on this face, and also on two perpendicular faces, this face and as well as this back face. All these values are minus P, correct? All these values are minus P, minus P, minus P, minus P, minus P, and minus P. Now, it's a state of triaxial stress, correct? It's a state of triaxial stress, and if you go to a bit of strength of materials, then you know your tau max is equal to maximum of you might be knowing this formula, I guess. Sigma 1 minus sigma 2 by 2, comma, sigma 2 minus sigma 3 by 2, comma, sigma 3 minus sigma 1 by 2. But now, in this case, what happens? All your principal stresses are same. Correct? If all these principal stresses are same, then definitely all these values turn out to be zeros. Correct? This is what you know. And in case of biaxial stress, you have only one formula, sigma 1 minus sigma 2 by 2, which we are talking in plane. Correct? So in that case, this answer is 0. Correct? Tau max is equal to maximum of all these things. Yes? So are you all clear? The answer for this question is 0. Please do type in the chat box, because the complete fluid is static and the cube is so small. So definitely, if the complete fluid is static, then there won't be any shear stress acting at any point in the static fluid. Similarly, there is no static stress that's act at any point within this cube. So definitely the answer has to be 0. Fine. Okay. So shall I go for the next question? India is going to lose, but I think it's going to win 4th and 5th T20s. Okay, no issue. Fine. Look here. Okay. So, shall we go for the next question? Is that clear to all of you? If you are clear, we'll go for the next question. Fine. Look at this question. There is something given. It's an old question actually, 96 something. A U-tube with both limbs open to atmosphere. So basically both limbs are open to atmosphere. I think there is no closing here. So both limbs are open to atmosphere. Fine. And this U-tube contains two immiscible liquids of densities O1 and O2. So you can see immiscible means they can't mix each other because of some densities difference, like water and mercury, or like water and air and all these things. Okay, they can't mix basically. So see here, two immiscible fluids. Immiscible means do not mix. They do not mix because of some densities difference or something. Then in the figure shown below, under equilibrium, the distance h is given by. So they are asking under the static equilibrium, of course, they are asking you for the what is the value of h. Then definitely if the complete system is in static equilibrium, let us apply a static balance about this section xx, static pressure balance. Okay, so if you apply on the left limb, you have P atmospheric local plus, and in density of A is neglected, so it's very small. So let us suppose this density is O2, it's given here. So this column is of height. Look, this total is L, this difference is H. So definitely this value is going to be L minus H, correct? So plus rho to G L minus H. This is the pressure at this point in the left limb. Similarly, at this point on the right limb, you have pressure atmospheric local plus dense pressure due to this column of length L of density ρ1. So ρ1 GL. This is what you have. So you can cancel this P atmospheric local in both the cases, and he is asking you for an expression of H. So if you want the expression for H, you have ρ2 GL minus H is equal to ρ1 GL. So GG gets cancelled, and ρ2 by ρ1, this value can be taken as, or maybe ρ1 by ρ2 you can write better, you will get a better sense. So ρ1 by ρ2 is equal to L minus H by L. So this implies ρ1 by ρ2 is equal to 1 minus H by L. So if you want this value, H by L is equal to 1 minus ρ1 by ρ2, and this implies H is equal to length times 1 minus ρ1 divided by ρ2. Correct? This is what you can write. So we have this value, and I think it should be in one of the options. Yeah, first option itself. Correct? L into 1 minus ρ1 by ρ2. Correct. Option A is correct answer, Rajneesh. Yes, option A is correct. Fine. So shall I go for the next question? Shall I go for the next problem? Is that clear to all of you? So shall I go for the next problem? Is that clear to all of you? Okay. So this is the first option. I mean, it's a very simple question, of course. So can I go for the next problem? Yes. Fine. So there is one question. In a static fluid, the pressure at a point is, you can tell the answer. The fluid is static. Look, it's clearly given it's a static fluid. First of all, if I say that the static fluid, if the fluid is static, will there be any concept of viscosity coming into picture? If the fluid is not moving, if the fluid is staying still, if the fluid is static, then please tell me, will there be any concept of viscosity that comes into picture? Will there be any concept of viscosity that comes into picture if the fluid is static? Yes or no? So please tell me, will there be any concept of viscosity that's coming into picture? No, correct? So viscosity doesn't come into picture. So with this, viscosity doesn't matter. Only if viscosity is 0, need not be. So this option is wrong. Always directed downwards. He is asking about the pressure at a point. Weight is always directed downwards, but pressure need not be, because at every direction, means in any direction, pressure is same. So you know that. So it need not be directing downwards. Next, equal to the weight of the fluid above. No. Look, because when the fluid is static, the pressure at a point, at this point, it's equal in all the directions, correct? Yes or no? It's equal in every direction. So definitely we can write this is the best option, equal in all the directions. Okay. So this is the most appropriate answer. So you can choose this, equal in all directions. In a static fluid, the pressure at a given point is equal in all directions. Fine. And the first sentence can be a bit, incorrect, because I'll tell you. If you see, if you take a free surface of liquid, let us suppose this is some free surface of liquid. If you take this point here, there is no water column beyond this, correct? But the pressure here is still atmospheric pressure. Okay. So here the fluid, he means the fluid is this fluid. Okay. So that there can be some ambiguity in its answer, but option B is definitely, a correct answer. Yes. Option B. Fine. So let's go for next question. So there is one more question. The dimensions of the pressure gradient in a fluid flow are. So the dimensions of a pressure gradient. I told you what is a pressure gradient, correct? Whenever I am deriving this hydrostatic law, I have defined you what is the pressure gradient. So let us write the units of pressure gradient. So dou P by dou X, which means basically the dimensions of pressure divided by the dimensions of length. So what are the units of pressure? Force per unit area. So force is mass into acceleration. Acceleration is meters per second square by area. This is the units of force, pressure divided by length is L. So if you take out this LL gets cancelled, and M L power minus 2 T power minus 2. These are the dimensions of pressure gradient. So is this option available at some point? M L power minus 2 T power minus 2. Yes, C is the correct answer. C is the correct answer. Okay, so the dimensions of del P by del X means basically del P by del X or del Y or del Z, any direction. So to generalize, you can take maybe nth direction for generalization purpose. Okay, so I am just taking this for the generalization purpose. In any direction. This value is always equal to M L power minus 2 T to the power minus 2. Fine. Okay, C is the correct answer. Yes. Undoubtedly, C is the correct answer. Yes. Okay. So let's go for the next problem. So there is one question you can solve. So two pipelines, one carrying oil of mass density 900 kg per meter cube and the other water connected to a manometer are shown in the figure. By what amount the pressure in the water pipe should be increased? Means here, what is the pressure? It should be increased so that the mercury levels in both the limbs of the manometer become equal. Look, he is asking you for, this is 20 centimeters. So if this is 20 centimeters, he is asking you there is some pressure. At this instant, there is some pressure in this water. So at this instant, if this height of the mercury in the right limb is 20 centimeters above, definitely if you increase some pressure of the water in the water pipe, then what happens? This mercury suffers some depression. Similarly, this mercury on this left suffers some inclination. Some raising, correct? Because this mercury is an incompressible fluid and the pipe, this tube volume is also fixed. So definitely, if there is some depression in the right limb of the mercury, definitely by what amount this mercury depresses in the right limb, same amount it should increase in the left limb. Correct? This is what you know. So he is asking you for by what amount the pressure in the water pipe should be increased so that the mercury levels in both the limbs of the manometer become equal. Look, by the time this both the limbs become equal, see carefully. Let us suppose case 1, P1 of water. Let us suppose if you are applying a static equilibrium about this point. If you are applying a static equilibrium about this point, see now, P1 water means the initial pressure of water, or maybe write P initial of water. Plus this water is of a height 1.5 meters, so density of water into G into 1.5 meters, of course, plus mercury is of 20 centimeter column, so density of mercury into G into 20 centimeters, which is 0.2 meters. This should be equal to pressure in the oil pipe plus this is completely oil of height 3 meters of 3 column, correct? So density of oil into G into 3 meters or 3. Let us suppose this is 3. Now, if you increase the pressure of water a little, then what happens? He is asking you for the pressure at which the mercury level in both the limbs of the manometer become equal. So if this is the case, look, here this is 20 centimeters. If both the limbs has to have same level of mercury, definitely out of this 20 centimeters, the mercury depression here should be 10 centimeters. Why? Because when mercury depresses by 10 centimeters in the right column, definitely there will be mercury level increase of 10 centimeters in the left column, and that's the reason both the levels will maintain, both the limbs will maintain same levels of mercury. Are you all understanding this point? Look, I am repeating this point. What's the main key point here? Definitely, if you want to have equal, heights of mercury column in both the limbs, this is 20 centimeters in XX. So that means this mercury column should reduce by 10 centimeters. At the same time, this mercury column should rise 10 centimeters. Correct? Yes or no? So let us suppose in the new configuration, let us suppose this is the section which we are taking. Okay. So let us suppose in the new configuration, let us suppose this is the section which we are taking and XX. So definitely this is 10 centimeters of mercury again on this side, and obviously this will be water completely in that case. Correct? So there will be some 10 centimeters increase in the mercury. So let us apply the static balance about this fluid now. This section XX. So if you write this equation, P final water plus, now this water is of complete height 1.5 meters plus 10 centimeters. 10 centimeters is nothing but 0.1 meter. So this will be total 1.6 meters, correct? So density of water into G into 1.6. So this should be equal to pressure in the oil pipe. This oil pipe pressure is not changing. Plus this oil is of now it's of a bit less density. It's a bit less height. So this is 10 centimeters. So 0.1 if you subtract, there will be 2.9 meters of oil column. So density of oil into G into 2.9. So this is the value. So what he is asking for, by what amount the pressure. So by what amount means this P final minus P initial. This is what he is asking for, correct? By what amount this pressure should increase. So P final minus P initial, what is this value? This is what he is interested in. So let us subtract these two. So if you subtract these two, what will happen? First of all, this pressure in the oil and this pressure in the oil gets cancelled. Fine. So if this gets cancelled, so P final minus P initial of water. So this is the amount by which you need to increase the pressure. So this value should be equal to, now second equation minus first equation. So rho water G 1.6, rho water G 1.5. So total this is, if you come onto the right hand side, minus rho water G 0.1. Correct? And this this is minus actually. So if it comes onto the right hand side, this is plus rho Hg into G into 0.2 plus this minus that value, which is minus density of oil into G into 0.1. So this is the value which you need to calculate. So now let us see what are the values that are available to us. G is known to us, given 9.81 meters per second square. Fine. What is the density of mercury? Mercury is 13,550. That's given. Oil 900 kg per meter cube. That's given. Water we know 1000. So let us substitute here. So if we substitute, let us calculate the values. So mercury into G into 0.2. So 13,550. So let us calculate this value. 13,550 into 9.81 into 0.2. This is the mercury column height. Mercury column pressure minus density of oil is 900. So 900 into G into 0.1. So which is 90 into 9.81. So minus 90 into 9.81. So this value minus, let us calculate, there is one more minus sign here. Density of water into G into 0.1. So 100 into 9.81. Let us calculate this. So minus 100 into 9.81. So this is the value. So you can see 24721.2. 24721.2. This is in pascals, but I think they are asking you in kilopascals. So 24.72 kilopascals. So here is the correct answer. Fine. So A is the correct answer. Yes. Sir, this week in YouTube class, what we will be dealing with? There is one case of manometers that we will finish in the tomorrow's class, and in tomorrow's class, I will also give you some introduction about hydrostatic forces on plane surfaces. Okay. So basically, this week we will cover. I mean, there are 3 more classes left in this week: Wednesday, Thursday, and Friday. So in Wednesday's class, I will talk about a bit of manometers. There is one case of manometers which was left actually, so we will talk that. And on Thursday and Friday, on Thursday I will take on the hydrostatic forces on plane surfaces, and on Friday I will take on hydrostatic forces on curved surfaces, by which we will finish the 3rd chapter. Okay, in 2 lectures. Fine. So see here, are you all clear to this point? This is the increase in pressure which you need to apply on this water pipe, so that you will have a 24. I mean, you will have both the limbs. I mean, both the mercury columns in both the limbs to be same. Is that clear to all of you? So please tell me, is that clear to all of you? Are you all clear till this point? Are you all clear till this point? So please do type in the chat box. Okay, fine. So let's go for the next question. Okay, I think questions are done. Okay, yeah, anyhow, time is also a bit short. Fine. So I think we solved some 15 questions. That could be a good practice on this manometers. Okay, and so as I told you, we have started offline. So we have also started the second batch, as I was telling you, on this Monday. So we have started with engineering mathematics. So by 2nd of April, I mean by the 4th of April, we'll be starting the core subjects. Okay, means basically as soon as this batch joins, we'll start. I mean, I think 29th is Monday again. So within next 2-3 days, we'll start the core subject. So please try to join these batches if you have passed out already, because in offline you'll be having person to person in guidance. Okay, and which you don't have generally in online. So I wish you would join definitely. And these are the timings as I tell you in every meeting of us. So 2 p.m. to 7 p.m. daily, 5 hours of effective coaching will be done. But of course, it includes some break in between for the recess. So 5 to 6 month program. It's a 5 to 6 month program basically. So we'll try to cover the complete syllabus in a very detailed pinpoint manner. And of course, the batch will also have some personal guidance from this All India Rank 1 of 2019 and 2020 XC papers. So and along with his team, we'll try to make it a big success for you. Okay. So anyhow, this is the classroom image that I generally show you, and these are the official contacts of Engineers Hub. So you can always find some YouTube. You can always find some useful content on this YouTube channel. And also, if you go to the YouTube channel once, I would like to show you once the official YouTube channel of Engineers Hub. So see here, if you click Engineers Hub, if you start typing Engineers Hub, so if you start Engineers Hub, so you can see here clearly. So you can see, you can find multiple playlists here. You can find multiple playlists. So for example, you can see this fluid mechanics course is completely put into one playlist. Similarly, this GATE 2021 analysis and this mathematics revision courses, there are a lot of contents actually. And of course, you can see there is one, particular playlist for job notifications as well. So you can find that. Just a second. I think it should be here. Yes. Yes, there is one playlist of job notifications as well. So we are updating what are the jobs that are available for engineers. So definitely we are updating it on time to time basis. And also you can see there is one in mathematics course, a comprehensive course that's done by me, and also some GATE revision course, means solving previous year questions, that's also done by me for engineering mathematics. So you can always follow these 2 courses as long as you study mathematics, because in this revision course I have solved some 700 plus GATE problems, and in this comprehensive course I have also given some effective 46 lectures on complete mathematics, which could be helpful for you. Similarly, there is also basic thermodynamics course by me. You can Yeah, these are the free courses available. I have also done complete basic thermodynamics course on this YouTube channel, which consists of some 25 videos. You can have a look at them, and if you feel there is some necessity, you can contact me again for some doubts and all. And also there is some study versus unstudy heat conduction, basically some transient heat conduction analysis by Nagy sir, and also some GATE 2020 solutions that are available. So basically, at the outset, I would like to tell you this playlist available in the YouTube, or means basically this YouTube channel of Engineers Hub is going to provide you a lot content in future, and also there is also a bit useful content that's already present on this channel. Okay, so and we are posting this class notes daily in this Engineers Hub ME Telegram channel, and also this Engineers Hub and ECA table, CAE, CSE, and all other branches. So you can get notes at these 2 points, and also all the video lectures at this point for free. Okay, as of now, and all the official updates regarding to Engineers Hub can be you can find them in the Twitter, Facebook, and LinkedIn pages of Engineers Hub, and also in the official website of Engineers Hub. Okay, so you can always get some useful data on what Engineers Hub is doing, and you can always get an update about its work in all these platforms. Okay, so okay, I'll try to provide these download options in this app. We'll do that. Okay, so fine. Thank you all. Have a nice time. We'll meet tomorrow sharp at 9:30 p.m. for our last lecture on fluid statics. Okay, on YouTube. Okay, that as I told you, theory lectures will be always on YouTube, and problem solving sessions will be on this Infinity app. Clear? Thank you all. Have a nice time. We'll meet tomorrow sharp at 9:30 p.m. Good night.